Okay, so hello everyone. Today we're going to be talking about a very empirical theme. I mean, the title of the talk, which is that why do you even need RLHF, which is a step in the pipeline of making systems like ChatGPT over SFT, which is another step in the same pipeline, right? So this all stuff is very empirical in the very initial stages. There are a lot of experiments going on. There are a couple of opinions floating online as to why this is so. But I think in order to provide more value, we'll be first diving into like what exactly is the motive of these two steps in the pipeline for constructing systems like ChatGPT, etc. And then we'll move on to discuss the various opinions that are there, along with some empirical works as to why we need RLHF over SFT. All right. And feel free to unmute yourself and ask any questions in between because I might not be able to just go to the chat box and see your questions. Right. So let's get started. So, as a primer, first of all, we'll discuss the base thing over here, which is that in order to be able to, deploy helpful systems like ChatGPT or these new models like Anthropic's Claude 3 suite, or there is like, of course, like new models are coming up every day. There are basically two things that we want, right? There are basically two aspects that we want to get satisfied. The very first is the capabilities aspect, and the second one is the alignment aspect. Now, elaborating on these two aspects, when I say the capabilities aspect, is basically the model is actually capable of doing what I want the model to do. And even if we drop the word model, let's talk about a system, right? A system like ChatGPT, or maybe a system like a very advanced chatbot that's deployed somewhere. This system has to be capable in the first place of doing the thing that I want it to do. Then only it will become helpful for me, right? If it doesn't really have the capability to do what I want it to do, then there is no point discussing the second step, which is alignment, right? First comes the capability. Now the capability aspect of these like huge large language models or whatever you call them systems is induced in these models at the pre-training stage of the pipeline, majorly at the pre-training stage of the pipeline. I think it's very important to mention majorly over here because now, as the Llama 3 report came out and as these new advancements are happening, there is discussions that the models even learn at the SFT or at the later stages of the pipeline, stages that come after pre-training. But we'll talk about pre-training here. So what happens is that the pre-training phase is basically the phase wherein you throw a lot of data plus a lot of compute to these sophisticated model architectures. So, mark my words, architecture is also important over here. You throw these things to these sophisticated model architecture, and what the model essentially does at this stage is what we call as unsupervised learning. It basically learns to predict the next token in the language, and that induces a lot of capability into the model, right? We'll discuss more on this, but yeah, that's what the capability aspect is for. You're basically giving a sense of the syntactic and the semantic structure of language to the model at this stage, right? Now, that is one thing, okay, that my model is actually capable of summarizing my text. It's capable of writing me a good creative story that's not plagiarized. It's capable of solving my difficult math problem. It's also capable of solving, it's also, let's say, capable of giving me very sophisticated intuitions on a theorem that I studied in my calculus class, which I'm not able to make sense of on my own. So that is like a lot of capability actually for a compute system to have. That is one thing. The another aspect of making these systems useful is the alignment aspect, which addresses the part that the model, along with having the capabilities to do what we want it to do, is actually following what we intended them to do. So that is also very important, right? Let's say I ask the model some question, and I just mentioned that pre-training deals with next token prediction. The model can just as well go and complete my sentence in a weird way. It might actually ask me another question, which is not what I want, right? So the alignment aspect, it's actually a pretty broad term. So like alignment is not just about following my instructions and being able to do the task that I ask it to do. It's a lot of things, of which one is the explicit part of it, which is that if I am asking my model to summarize something, it should actually give me a summary of it rather than an elaboration of it. So that is like the explicit aspect of alignment. But yeah, alignment, we can think about alignment in terms of having the model to follow or maybe to stick to human preferences. That's basically how we can define alignment. Of course, there are other definitions as well. There are other ways to cover this very broad term, but yeah, this is one way to talk about it, right? So, as I mentioned, there are two things to alignment as well. The one is very implicit, one is very explicit. Explicit, as in the model is able to do what I'm explicitly asking it to do. I would say that, okay, now this model is aligned to my preferences. Another thing that is there, it's is very implicit, right? It's that the model is not outputting gibberish, it's not making stuff up, it's harmless, it doesn't talk about sensitive topics, it's not biased, etc. and etc. Like I could go on and on. There are a lot of things under this implicit umbrella of alignment. But basically, the idea over here is that there are two things that are needed for these systems, like for these language systems or these dialogue systems to be useful to us as humans. One is the capability aspect, which is majorly addressed at the pre training stage. The second aspect is the alignment aspect, which actually comes after pre training. Now, let's talk about the reason why we need to discuss the alignment step, which is also one part of making these systems useful to us separately, right? Why can't we say that, okay, when I am pre training my model for the capabilities aspect, why can't it also learn to, you know, follow my intentions or maybe do just what I wanted to do, right? So that is like a viable question over here. So, and the answer to that is actually pretty simple, which is that these pre-trained models, like when we are pre-training the models, what we are basically training them for is just a very simple like task, which is just next token prediction. We're telling these models to sort of learn like a conditional probability distribution over our massive data, which sometimes is actually whole of the internet. We're just throwing all of this data to the models without any filtering mostly, and asking the models to sort of just, like learn this probability distribution over these tokens. What that also means is that because of the fact that I'm not filtering this pre-training data, this massive data that is actually inducing a lot of capability into my model, it is also introducing a lot of bad actors into my model. Like there is no filter as to what I'm throwing at my model. This data could consist of some brilliant pieces of text from, let's say, some textbooks or let's say some very sophisticated discussions online, but it could also consist of a lot of hate speech, a lot of racism, a lot of bias, a lot of, let's say, toxic info or maybe info that is sensitive to talk about, some stuff that you would not really talk about as it is online. So a lot of stuff is present in this data, and we're just telling the model, like we're just training the model to learn to do next token prediction, and that is all. There is no sense of human preference that we are inducing into the model at the pre-training stage, which is why there is a need to discuss alignment separately from the pre-training stage, which is what we are calling the capability stage majorly. Like I'm not saying that, okay, SFT is not capable of, like inducing any knowledge into the model. The same for RLHF, because of course papers are out there, discussions are out there, but I hope I get the idea across, right? So the gist over here is that the data that we are using for the purpose of pre-training is not always aligned with the end consumer of these, let's say, products of these systems, right? And if we look at actually this one very, I think, like very outstanding statement from an OpenAI technical report, it says that OpenAI says that our labelers prefer outputs from our 1.3 billion instruct GPT. So mark this over here. This is just a 1.3 billion model, which had something on top of pre-training as well. And the laborers tend to prefer outputs from this model more than GPT-3, which is a massive 175 billion size. That's like, I think, more than 100 times of parameters difference between these two models, right? But this 175 billion GPT-3 that they're talking about is just pre-trained. It's just pre-trained on massive data from the internet along with a lot of compute. And so that is there. So these things are actually, I think, enough to give an intuition as to why alignment needs to be discussed separately from the pre-training stage as we have it today, which is basically next token prediction, right? Okay, so that is there. And are there any questions so far? You can like feel free to unmute yourself and ask anything.
Yeah, so there is a question. I'll go ahead and read it. It's from Harsh. It's a rather long question, but I think we can track it. The question is regarding alignment. My company has a database of customer queries, and our support answers are in it. The data set's not very large. Let's just say it's 1,000 pairs of questions and answers that are more of a conversation as opposed to, I would think, a Slack communication or something like that. And I tried to fine tune the Mistral 7B, but it couldn't learn the information that we had in our answer. Like, say, we wanted the model to learn how to navigate our web pages. How do we align on small data sets or use case only works with RAG?
Okay, I think that's a very like experimental kind of question. So I would say that when you say that we tried to, make the model to learn how to navigate the web pages, you did some sort of fine tuning. Now, fine tuning also comes in two flavors. It could be like full fine tuning, or it could be some form of parameter efficient fine tuning, wherein you are like, um, like tuning or maybe training just a part of the model. So a lot of factors go into deciding and go into experimenting with this kind of a thing, whether or not the model will be able to learn this kind of a task or not. But I think it's very hyperparameter sensitive also. And RAG can definitely be done, but I wouldn't conclude that fine tuning is not at all useful for this kind of a task, right? I'll have to actually see your experiment and your logs, the hyperparams you used, the fine tuning technique you used, and also like the size of your base model along with the quality of your data is actually pretty important. If you throw garbage to the model, it's going to learn nothing but garbage. And what also goes hand in hand is the objective that you specify for learning, the loss function that you use. It also has to be correct both mathematically and intuitively. So I think that's enough to answer the question.
Excellent.
Yeah, okay, no worries. Right. Now, so I've been mentioning these terms SFT, RLHF, and all of these things. I want to also take a moment to just go over the standard pipeline that goes into deploying or like creating systems like ChatGPT or maybe these new models like Anthropic or whatever are coming up these days. So what happens is that the pre-training stage, as we call it, is all about unsupervised learning. Now, when we say unsupervised learning, what we actually mean is that we're training the model just to do next token prediction. So I'm just training my model. I'm training a system, a model who's very good at completing my sequences of text, who's very good at predicting what come next in a sentence like this color of the sky is dash. My model is actually pretty good at this, and that's what I'm training it to do in the pre-training stage. The reason why I call it unsupervised learning is because while I'm training the model to do next token prediction, I am nowhere training my model to summarize my text, to write a creative story for me, or maybe to solve a math equation for me, to explain a math equation to me, to debug my PyTorch code, so on and so forth, right? Those are not the things that I teach my model to do in the pre-training stages of the pipeline. And even like despite this fact, the model is actually able to become very good at these tasks. The reason behind that is distribution matching, which we'll not discuss a lot today. But that's the reason why we call it unsupervised, because we don't really have any labels for summarization or maybe debugging the code or a plethora of tasks out there that you can think of in the pre-training stage of the pipeline. We're just training the model to do next token prediction, and that's it. The result of which is that the model actually becomes very good at completing sequences of texts, right? That's the result of that. And here I would also give some intuition as to why unsupervised learning might work is that, we can formulate a lot of tasks out there like summarization, debugging a code as completion tasks. But that's not, I think that's not the core reason over here. The core reason is distribution matching, which you can read about more later, of course, right? So, and now we were saying that, okay, this is the capabilities aspect. I'm teaching my model to become very good at completion. But then I also mentioned that just teaching the model to be very good at completion might not make these systems useful in the sense that we discussed above. I mean, actually, it's a very big part of it. Of course, we're inducing a lot of capability into our system or our model, but that is just completion and that's all, right? So a scenario could happen wherein I ask my model or my system a question, how do I learn CUDA programming? And it could go on and complete my task in the way that we see on the screen, which is that it could ask me another question, what are the best MOOCs available? This is actually a viable completion. I can never question my model. I would never say that, okay, my pre-training went wrong because the model wasn't really able to answer my question. No, it did not go wrong. It was actually pretty correct because this completion is actually pretty viable, but not useful in the sense that we discussed above, right? Not useful because here the system didn't do what I intended it to do, which we're going to cover in the alignment phase of the pipeline, which consists of two basic steps. The first one I'm going to discuss now, which is called SFT, which is supervised fine tuning. Here, what we essentially do is what we call as behavior cloning in our literature, but let's stick to SFT for now. We would basically take some data. Now, if you just go back to what I was discussing a minute later, unsupervised way of teaching the model in the pre-training stage, here the way is actually supervised, which is actually well addressed by its name, supervised fine-tuning. We're going to take data that has both the prompt, the questions, or maybe the task, whatever you call it, that one might give to these systems, along with the completion of it, along with, the most appropriate answer of it according to some expert human, right? We do take such form of, let's say, XY data, wherein I actually have proper labels in place. Labels here would be the completion part of these pairs. And then we fine tune the model using this data. The result of it is that the model now gets steered in the direction where it's actually able to do dialogue kind of, like question answering kind of thing with me, or maybe becomes good at following the instructions that I give to it, which is called instruction following basically, but I'm avoiding using that term because again it consists of two three things over here. But yeah, SFT, a result of SFT, which is supervised fine tuning, could be that the model actually becomes good at completing my prompt in the way I intended it to do. And that is the result of this step of the pipeline, right? Now that is there, okay? Now, a question over here is that I think that's all. That's all. Like, we had a very good system, which was very capable of doing the tasks that we wanted it to do. Then we also steered it in a direction where it's able to follow my instructions and do what I intended to do. And I think then that we should be done, right? What's the need of this another very fancy and I would say very computationally intensive step, which is called RLHF. We'll come back to the need for RLHF later, but let's discuss what RLHF actually is. in a minute. So what happens is that our end goal of alignment is to include human preferences into our this system, this model that we have at hand, right? And that is exactly what we do as a first step. We would collect preference data. I mean, we would just use this SFT model, ask it some questions, give it some prompts, or maybe give it some text, and then take the completions of it. Two, three options out there, or maybe like six, seven options out there, give it to some human who would then rank these responses. And then we'll have preference data at hand. Basically, we'll have human preferences at hand, wherein humans are actually involved in ranking these responses. Then we'll use this preference data to train a reward model that would now act as a proxy for humans, because of course you can't just keep using humans and humans, right? That's very expensive. So we train a reward model for this purpose. Then we again use the SFT model, which in RL literature will be called the policy now that we are discussing RLHF. We use the SFT model to get a response corresponding to some prompt or some question that I have in my data set. Then I take the model's answer to my question, send it to the reward model that I just trained in the first step, and I get the reward back. Reward in the sense how good was the model completion actually. That is the work of the reward model to do. Then we take these things, this reward, along with like the prompt and the response, and we then update my SFT model according to this reward. So the gist of it, I mean, this is a very complicated pipeline actually, and not actually so complicated, howsoever. But I think oversimplified it over here. But the takeaway from this slide, the gist of the RLHF pipeline is that we're just taking human preferences and inducing it into our SFT model. That's what we're doing. So rather than just, um, making the model to follow some data set, we're now having human preferences in the pipeline, more in the form of a comparison and the reward model step. But yeah, that's there. Now I'll come to the main topic of this talk, which is why did we need RLHF over SFT? The time is also up. I think it was 30 minutes, but yeah, let me just go on for 5 minutes more. So as I said, that we wanted the model to just, like become good at following our instructions, and SFT should be good enough for this task. Then why do we even need RLHF? So let's start. So let's say in the data set that I use for SFT, I have a prompt completion pair that goes like, give me a funny answer as to why learning is hard, or maybe a sarcastic answer as to why learning is hard. And then there is also a gold ground truth answer to that in my data set, which is actually the why of it, the completion pair. And then that's it. There is just one correct answer that we are penalizing our model for. But there could actually be many different answers to this one question or to this one prompt, which is not well addressed by SFT, right? So that is one kind of a plausible explanation as to why SFT is not the perfect thing over here. But not too convincing, right? Because SFT models actually have performed well in practice. Like we've seen it a lot, right? So, and then we come to the next point. A more convincing point over here is that when we do SFT, we're basically doing behavior cloning. We're showing the model what it has to do or what we want it to do. But during SFT, we never show the model what it should not be doing. That step is actually better addressed by RLHF, because therein we're actually sampling from the model, and whatever the model is going to give out might also get a negative reward from a reward model that would teach the model what it should not be doing, in addition to teaching the model what it should be doing. The latter is what SFT teaches, and that's all. So that is also like one important point as to why SFT might not be just enough, right? A related point is exposure bias. So what happens is that when we are just doing supervised fine tuning on top of our pre-trained model, we are giving it all the good things, right? Like we're just teaching it what it has to do. But what happens is that in practice, when we deploy such a system, it might come across something that it did not have to do, but that step was never addressed in the SFT pipeline. So that's kind of an exposure bias, a discrepancy between the training step and the test step, which might cause the model to actually deviate more and more from its intended behavior, which is what actually happens. While what happens during RLHF is that the model is generating its own responses that are getting rewarded by the reward model. So, in that step, the model is actually also getting a sense of what it does not have to do, right? So, that is also one, I think, very cool point over here. And an outcome of that is also that RLHF hence has the ability to outperform the data set that we have at hand. Whereas that's not really, I think, possible during SFT, the outcome of which is the generalization aspect of these two steps of the pipeline. We've seen it in a very, I think, not a very recent, but it's actually a paper out there by Robert Kirk at Meta that actually proves it that RLHF systems generalize better than SFT systems. The reason is that only, and that especially on out of distribution data. The reason is that only that during SFT, we're just teaching the model what it has to do, not even showing the model what it does not have to do. There is this exposure bias, which is again a broad term, but in a nutshell, I've explained it. Because of that exposure bias, RLHF systems tend to generalize better on out of distribution data, which is not the case with SFT models, right? And I think like that's it. Those are like the major reasons why we need RLHF also on top of SFT. There are actually many things to discuss over here, like what RL algo do you use for RLHF? Is it PPO or is it some other algorithm? PPO is actually pretty expensive. It's a non-policy algo, but those are the things that are not the scope of this talk. A very like a minor thing that I would also like to mention over here is that what we are doing during SFT is again the cross entropy loss, something kind of similar in essence to pre-training. And so what we're doing is actually distribution matching only during the SFT stage, which is what we also do during the pre-training stage. Whereas while doing reinforcement learning, we're kind of doing a thing that is inducing human preferences into our base model. We're biasing the model towards human preferences more when we do RL or RLHF. A downside or a negative outcome is that the model now becomes sort of like mode seeking. The diversity of the model, like the diversity of the tokens that it produces, kind of reduces because of RLHF, which is also proved in this same paper that I'll send in the chat in a while. But yeah, that's there. With RLHF, just because we're inducing kind of a bias in the model, bias, like we're making it biased towards human preferences, its creativeness aspect, like the diversity aspect, reduces in comparison to SFT. And I think that's all.
Uh,
So, already
Fantastic.
up.
So I think I may have jumped the gun, but let me know if I got the right paper. It is Understanding the Effects of RLHF on LMM Generalization and Diversity by Robert Cook at Meta. Let me know if that was the right paper.
Correct. That's the
Okay,
correct.
so I've gone ahead and posted that in the webinar chat, but I'll also post it in the follow-up in email as well as summary blog posts. It does look like you do have 3 questions if you want to go ahead and tackle those.
Yeah, sure. So, does SFT generalize to multi-level conversation? So, I think this is talking about like some chat history in place along with the current question that we want the answer to. So, of course, if you have a data set like that, if you can construct actually a pretty good data set like that, you can steer your model in that direction. But then, talking about generalization, as I've already addressed, RLHF might be the better step for generalization as compared to SFT. Right. Okay, what's the architecture and complexity of reward model? It is the same as our main model. Good question, actually. There are a bunch of choices out there. DeepMind, I think, use a model for reward modeling that was the same size as the base model, but like different companies have experimented with different sizes and architectures of reward models. So there are actually different choices available. But the rationale over here is that the reward model should be pretty capable of, understanding the data that we're giving to it, so that it becomes good at giving the rewards. It acts as a good oracle or a proxy. So yeah. Can you suggest any good video link to try SFT and RLHF on sample data sets on a selected model? So yeah, for I think you could actually look into the Hugging Faces repo. We have the SFT trainer out there in the TRL or TRLX library of theirs. I think those are pretty good and quick places to start for this kind of thing.